Hi, everyone, and welcome back to the MTV Nuclear Engineering Summer School. We're happy to have you for today's final lecture in this summer's series. Our speaker will be Dr. Ciara Sivels, who is a graduate from this department of Michigan Nuclear Engineering. And currently, she's working at Johns Hopkins University Applied Physics Laboratory and as a staff scientist. And today, she's going to give us an overview of the research activities that are undergoing there. So if you have any questions, please put them in the chat along the way, and we will address them at the end. So with that, Ciara, please go ahead.
Okay. So hi everyone. This is my first time talking about APL, so please let me know if you have questions. Please put them in the chat because this will be good feedback for the lab. So like Sean mentioned, I'm a graduate of Michigan. My research was in radio xenon detection, and I did experimental work as well as simulation work. And here at the lab, I focus more on simulations. And so a lot of the stuff that I do here, I can't talk about specifically, but I wanted to just kind of give an overview of like what the lab does, where nuclear engineers can fit in, and I'm gonna show some of the postings that we have. So I will go ahead and get started. Or try to get started. Okay, there we go. So what is APL? What is our mission? So this is one of the big themes for APL, and that's critical contributions to critical challenges. And so here at the lab, we're really trying to, figure out what are the up and coming innovations that our nation needs to focus on in the 21st century. And so because we are a UARC, and I will kind of explain what that is in later slides, we collaborate with a variety of entities, whether that's industry, government, or academia. And we really focus on areas of national importance. And we're also committed to public service and like giving back to our community. Okay. So some history about APL. It was founded in 1942, and it had the mission of developing the VT fuse, which I'm not sure if any of you are familiar with, but it was a technology in World War II that basically, it was a missile that was created so that as you got closer to your target, it just exploded. And that was that was a first step in doing missile defense with guided missile technology. And so because of the success with the VT fuse, the Navy requested that Johns Hopkins create a separate entity, and that entity became known as APL, and it became a permanent division in 1948. So as I mentioned, it is a university affiliated research center, also known as a UARC. What we do here is we kind of have staff members that are combined with technical skills and have goal orientation. So a lot of engineering work goes on here, but it's also a very objective type of entity, so that it doesn't really have an industry focus. Some of our sponsors are the DoD, NASA, Homeland Security, and we work a lot with the intelligence community. And as I mentioned, the motto here is creating critical contributions to critical challenges. And so some statistics about the lab: it has about 8,000 staff members, and you can see how much in revenue the lab gets. And so what does that mean when I say that we're UARC? So I have here at the bottom, you can see that APL is the nation's largest UARC. And so we sit at a very unique position. So we're not academia, we're not industry, and we're also not a national lab. We kind of sit in the middle of all of those things. And like I said, our biggest sponsor is the DoD. And so we work a lot with the government and making sure that we understand what their requirements are. But we also have access to a lot of info and proprietary information that can be sensitive. And so that's where you get into a lot of people here just can't talk about what they do because of that, because of the nature. But because we are in this unique position in between kind of industry and academia, we get to do a lot of research and a lot of independent work separate from the government and as it pertains to contracts. And so I'll talk a little bit more about some of the specific tasks that we do, but this kind of gives you a overview of kind of what our relationship is with the government and what a UARC actually means. So here's some of the demographics. So something that's also different for us than say a national lab is that the majority of the staff have master's degrees or bachelor's degrees. And if you think of national labs, the majority of staff there typically have doctorates. And so that's something that's kind of unique to APL in that when you come in as a, say, master's, and especially if you come in with a PhD level degree, you come in as someone that is considered senior. So you come in with already 5 years of experience under your belt. And so here at the lab, there's a big push to bring in more PhDs because you have kind of this expertise and this trained way of thinking that's unique, especially when it comes to innovation. And so how can you use your skills and combine those with the needs of the government and the lab to solve these challenges and think about the next generation of technology or the next algorithm that could be cutting edge. And so you can see on the left too, about 80% of the lab is built up of technical professionals. And as I mentioned previously, most of the background is in engineering. And so in a later slides, I'll also kind of hit on where nuclear engineers kind of fit in the lab. But you typically see a lot of systems engineering here. You do see a lot of physics and math backgrounds, a lot of computer science, and a couple of mechs and electrical engineering degrees as well. So this is a big list of APL's 12 mission areas. So I'm not going to go through all of them today. I'm going to hit on the ones that specifically relate to nuclear engineers. But some of the other ones that people, when you hear applied physics lab, I'm not sure what people think. I know when I first heard of it, I thought, oh, it's like a bunch of physics experiments. But like, as I mentioned, the lab was actually founded on missile technology. And so the air missile defense mission area is one of the biggest focuses here at the lab. But we also, especially with COVID, we did a lot of work in the national health arena, especially working in collaboration with Johns Hopkins and just getting the data and statistics and better understanding how the pandemic impacted a lot of things. And so APL actually did a lot of studies during that time. But some other mission areas that I won't touch on today are things like sea control and precision strike and special operations. So these mission areas typically fit in our force projection sector. And so that sector is basically the antithesis to air missile defense. So what that basically or really consists of is our offensive capabilities. And so as you can imagine, a lot of that work is not widely available or distribution A. And so a lot of the stuff that I'm going to talk about today is public knowledge you can find on the APL website. And so, yeah, but these are the overall 12 mission areas. So I'm going to start with the Homeland Protection Mission Area because I think this most closely aligns with the work that I was doing previously at Michigan, a lot of non-proliferation work and verification work. So within the mission area, the overall goal is kind of to protect the nation from asymmetric threats. So that's, hidden attacks and basically make sure that we are staying competitive against our global competitors. And So the way that we do that, again, is just working collaboratively with industry, like I said, government and academia, to try to make sure that we stay innovative. And so you can see at the bottom, the big focus is to create capabilities that basically safeguard and secure the homeland. And so how do they do this? So these are some examples. Of course, countering the weapons of mass destruction. We also have cyber and communication systems that we focus on and make sure that even in, say, a perturbed environment, we can still function through our systems. And then also, we work very closely with the Army and working to create surveillance and physical security systems. And so what you all are probably familiar with is this specific program area. We work a lot with national labs here in this area. And again, we also, in addition to doing detection work, there's an emphasis here at the lab on really AI and how do we do machine learning and how do we make these processes automatic so that we can remove the human in the loop. And so one example of this work is shown in this picture here. So APL was a recent winner of a 2021 R&D award, and this was for a multiplicity counter for thermal and fast neutrons. And again, like I mentioned, APL does a lot of collaborations, and so this was in collaboration with RMD and Lawrence Livermore National Lab. And so there are some alum from Michigan that actually work in this group. I think one of Professor Posey's first or second students, Eric Miller, also works in this group. So there are nuclear engineers in a variety of spaces in the lab doing a variety of work. So this is the first kind of example that I wanted to present. So the second example is the civil space mission area. And so within this mission area, there's a lot of examples and ways that nuclear engineers can kind of impact how we travel from the sun to Pluto and beyond, and how we do research in this different arena. And so here at the lab, we focus on the beginning to the end of the space mission. So we do everything from prototyping to research to testing to even generating proposals for space missions. And so nuclear engineers play a vital role in this arena because not only does the system have to survive in, say, a radiation environment, but there are also examples at our show in which some of the detection capabilities are also used on these systems. And so this is another mission area that is heavily influenced by nuclear engineers here at the lab. And it's also, like I said, APL was kind of founded on the missile technology that we developed, but this space sector has really grown. And as you'll see, we've acquired a lot of funding through the space sector in the work that we do and how successful these different missions have been. So the first example of a mission that APL was involved in is New Horizons. And so New Horizons was launched in 2016, and it has been flying ever since. And so it was the first mission to Pluto. And so it was revolutionary in that way, in that it showed a bunch of capabilities about how we can get information about the solar system. And it's, like I said, continuing to travel beyond Pluto, becoming the farthest flyby in history. And so this first kind of project that APL in the space sector was involved in really put us on the map to sort of do more cutting edge space travel. So moving forward, we have the Parker Solar Probe, and I'm not sure if people have heard much about this, but this is a really big deal for APL because this is the closest, one of the closest systems that has gotten to the sun. And so all of the spacecraft systems, like the thermal protection system, everything there is operating as it's continuing to get closer. And so this really highlights something that we focus on a lot here at APL is how do these systems behave in these very hostile environments, whether that's temperature, whether that's radiation, right? And not only does your protection system, so that material that's covering your spacecraft, not only does that have to operate, but also the electronics within the spacecraft have to operate, and the sensors on the spacecraft have to operate. And so here at the lab, something that I've learned very quickly is that all sensors kind of work the same. They're just measuring different phenomena. And so a lot of times as nuclear engineers, we are looking at, say, the particles and how they interact with the detector. But a lot of these sensors are light sensors. And so there's a combination of physics that's happening that you have to kind of account for, because now you have particles and light that have to work in competition to still get the information that we need. So this is the most recent launch that APL has had, and was this was a cool project because it built on APL's missile technology, and so it's the first defense mission. And so basically, what DART is doing is they launched it to hit an asteroid, and so this DART stands for the Double Asteroid Redirection Test. And so basically it's using an impactor to change the trajectory of the asteroid. But like I mentioned, it advances a lot of technologies. One, that SmartNav technology is founded again on the missile defense and guided missile work that APL is founded on, as well as new imagers and propulsion systems. And so DART is something that APL was the lead on, and again, is an innovative task in that it's NASA's first planetary defense test mission. And so it's coming up pretty soon, the impact, a little over a month and a half. So we'll be having another kind of watch party to see what happens when DART makes its impact. And then I think this is the final example that I have for civil space. Civil space is Dragonfly. And so Dragonfly is APL's, I guess, probably biggest funding project to date. It is the first rotorcraft mission to another world. And so it is visiting Titan, which is one of Saturn's moons that has a very dense atmosphere, but also has some elemental compositions on the surface that we want to measure. And so again, this is another example of how you have a system that not only has to survive and operate in a hostile environment, but then on top of that, they've added a gamma ray and neutron spectrometer, which again is very relevant to nuclear engineers, and especially those that are doing detection work like I was. And so it basically has a neutron generator that it pulses the environment, and then you read back the gamma ray signature to get a better understanding of the composition of the samples in the soil there on that moon. And so this task is also led by APL, and there's a bunch of radiation engineers that are doing testing currently to ensure that the electronics survive, that the material survives. And so within civil space, what nuclear engineers typically there are doing are a combination of experimental work as well as simulation. So there's a lot of MCMP work that goes on, but there's also a lot of ion beam testing and things like that. So making sure that we get a feel for whether the dose rate levels for the electronics that we need to function in these environments, how does the material properties change as these systems are radiated and as they're traveling through the space environment. So that's kind of a summary of what work nuclear engineers kind of do in the civil space area. And there's a bunch of other missions that APL has been involved in and spacecraft that APL has helped develop and test. Okay, and so then I'm going to spend the rest of the talk talking about the air and missile defense sector, which is the sector that I work in. So as I kind of started off this talk, the air and missile defense sector has a long heritage. It's kind of what the lab was founded on, starting with the proximity fuse. We've done a lot of work looking at anti-air warfare and the missile development of that. And I can answer more questions about this work offline. We also did a lot of development with radar, cooperative engagement. So how do we make sure that our ships are all talking and their information is fusing together? The biggest thing that I work on is ballistic missile defense. So how do we make sure that our defense mechanisms are in place and operate and function the way that we need them to? But looking forward to what we're trying to do in the future, and I'll talk about this a little bit later, you can see on the right-hand side, we wanna make sure that we're always defending the homeland, we're dominating space and near space, and we're also operating and functioning in congested environments. So this is just an overview of some of our leadership roles as the air and missile defense sector. So I am not necessarily familiar with all of these, but these all play a big role in how air and missile defense operates. Specifically, I'm familiar with Aegis BMD, so that's Aegis Ballistic Missile Defense. And so that's how we launch things from the sea. There's also standard missile and ground-based mid-course defense, and that's how we launch things from the ground. And these things all kind of work together with radar and cooperative engagement. So this is kind of what I wanted to highlight in my talk and mentioning about UARCs is that because we are in a very, like I said, unique position in between kind of industry and academia, we're often tasked with being this leadership position in between government and contracts. So a lot of times when these new systems are coming on board, typically there's a contract process that is happening. So the project that I work most on these days is the next generation interceptor. And so right now you have two companies that are competing for the government contract to develop this new interceptor. And so what we do as a technical directorate agent here at the lab is we make sure that the contractors are following the requirements. We make sure that we understand the concept of their system that they're proposing. And then we do independent assessment. So we go through and we run the calculations to say, hey, they said that their system can perform X. So we do the calculations to make sure that that's true. If there's a discrepancy, we bring that to the government and things like that. But we also do our own research on the side. So we create what are known as government reference concepts. So in addition to the contractors in their proposal, we create a concept to basically show the government that, hey, what you're requiring from the contractors is feasible. And so as the direction agent, we kind of are the liaison between the two to say, hey, these are the things that are high risk and things that you should be paying attention to. These are maybe the parts that need to be tested. These are maybe the requirements that have a higher hierarchy than other things. And so we originally were the TDA for Aegis BMD, but in the last year, like I said, when NGI was being proposed, we became the TDA for GMD as well. And so one of the things that's important here for us, and like I've been mentioning throughout this talk, is that these systems have to operate in hostile environments. And so there's a lot of phenomenology that goes along with that, but radiation is a big part of it. And so as nuclear engineers, we are looking to apply models in SIM to make sure that these defensive systems and the new proposals that are coming out can fit the requirements and do the job that they're expected to do. And so again, these are kind of our grand challenges going forward. And so it's kind of hard to see in this figure, but what it's showing here is you have your communication to your ships from, say, your satellites. You have your enemy that is launching missiles and things towards your ships, and then you also are trying to defend that, but you have a lot of it going on at once. So that's what they mean when they say pure conflict in congested environments. How do we make sure that we can successfully defend ourselves in such a congested environment? And so that's that's all a part of defending the homeland, which is here in the center. And then really forward thinking is, how do we dominate space and near space? So you see this image here that's hypersonic. You have a bullet hitting a hypersonic. So a lot of original missile defense was this idea of hitting a bullet with a bullet, right? And so when you start talking about hypersonics, and things that can maneuver, it's not as simple as that. And so how do we make sure that we are constantly staying abreast of what our peers are developing and making sure that, again, we can defend ourselves in the homeland? And so some strategic vectors that we focus on are transformational command and control. And so again, that's, how do we link all of these things together? Looking at novel kinetic weapons, as I mentioned, like with hypersonics being a up and coming technology, how do we best defeat those? Ubiquitous ISR&T. So that's how do we use the intelligence that we're learning from the intelligence community? How do we fuse that into our targeting and our surveillance? And then how do we tie that in? How do we fuse all of that information together? That's kind of what the cognitive communications and networks strategic vector focuses on. And then you see asymmetric non-kinetic defeat. So these are other ways to do defeat that are not using this system as an actual weapon. And so I wanted to post here and show some open positions that we have. So this is probably as close as I can get to talking about kind of the work that I do. So this is a position that's open right now in the group that I work in. And we're kind of looking for people with skills in MCMP or JON, of course, having a background in nuclear engineering. But the focus is really on how can we study effects of nuclear weapons. How does that affect our systems, and how does that affect air missile defense? And as I mentioned, we have a similar call for the alternative, which is the force projection sector. So similar thing, how can we best align ourselves so that we are accounting for nuclear weapons effects and their impact on our strategic systems? So some other things about APL, it is Howard County's largest private employer. Um, a lot of people from the area, especially, it's very interesting, like a lot of say like people that know about the lab are because they are from the area. So we're trying to change that, and we're trying to get the lab in more of a forward position so that people understand that there's a lot of work going on here at the lab. And so one of the things that we do is because we work with industry and the government, is we do develop a lot of intellectual property and patents. Um, and that's just, again, because of the unique position that we're in between industry and academia. And so there's also been new companies that have been created from work done at the lab. And APL actually has a program where they allow staff members to go off for 2 years and work on their startup based on, say, some technology that they started here at the lab. Um, so one of the other things that I really enjoy about APL is they have a built-in STEM program office. And so I did a lot when I started here. I did a lot of outreach with them. And then I also was a AAAS if then ambassador. In the lab, through the lab. And so that allowed me to work a lot, the STEM program office and the communications team here at the lab, coming in and having people visit and doing demos and, filming different things here at the lab. And so APL is very focused on making an impact in this area. And so then talking a little bit about our UARC status, because we are university affiliated, we also do a lot of collaboration with Johns Hopkins. Although we are, like I said, our own separate entity from Johns Hopkins, we have mechanisms put in place to collaborate. So we have people at APL that do hold joint appointments as professors at JHU and as staff members here at the lab. We also bring undergrad and graduate students to do research at APL and vice versa. We have people that come in as master's students and get their doctorates while working at APL. And then on top of that, like I mentioned, people taking extra courses. So there is a built-in Whiting School of Engineering that is specifically for part-time students. And so we have a lot of people at APL that teach these courses. And I've actually taken a few courses myself through the Whiting School of Engineering. But it's, again, another way that, because we are UARC and because we are affiliated with JHU, we always have this motto of you never stop learning. And so there's all these different opportunities to, say, get additional degrees or even just learn new things. And so here's just a picture of APL's, this is the main campus here. And then this is our new South Campus that's been built. And then this is not a good representation of the MP campus, but there's about 6 buildings on the MP campus as well. And then I also have a video that kind of summarizes APL, but I kind of want to give a little bit more time for questions since I know a lot of people aren't as familiar with the lab. So I will stop talking now and I will take questions.